Going once, going twice. Okay, so last time we started talking about limits, and we left off with the definition of a limit. So everybody has it memorized?
Yeah.
Yes? Okay, pop quiz. What is it? All right, so the short. Okay, I should probably point out one thing now that I guess I said on Monday that I said on Wednesday that Monday we have a day off, right? Because it's Labor Day. I should probably bring to your attention that on Thursday, so a week from yesterday, is the Census Day. If you're not familiar with the Census Day, it's the last day to add or drop or change sections or any of that fun stuff. So we're basically encouraged to inform students about that. So you're informed now. Okay, short. Short version of the precise definition of a limit says that the limit as x goes to a of f of x is equal to L is equivalent to saying that for every epsilon bigger than 0, there is delta bigger than 0, so that if 0 is less than the absolute value of x minus a is less than delta, then the absolute value of f of x minus capital L is less than epsilon. So this is what we talked about last time, right? This is basically like the last thing that I put on the board. And so the question of the day would be, what exactly does this say? And the answer for that is that it actually says exactly what we said as far as the non-mathematical definition. Remember what the non-mathematical definition of a limit was? You know, like the actual verbal definition. It said the limit is L if I can make f of x be as close to L as I want to by making x necessarily close to A. Remember that? Well, that's exactly what this says. This basically says for every epsilon there is a delta, which basically means for every epsilon, which shows up in here, which means tell me how much far away you want to be from L, right? So tell me how big of this distance has to be. That basically says, you know, for every epsilon. I can find a delta, which means I can find some other number for which this distance is small enough for that to hold. Graphically speaking, it should probably make more sense. So if I have this lovely function, whatever the function is, let's call this number here A. This is going to be capital L. What this definition says, it says that for every epsilon, so pick just some random epsilon, if you think about it, let's see, if I look at this particular point right here, this would be L plus epsilon. You look at this point below here, this is L minus epsilon. Okay? Why is that representative of what I just said before? Well, because think about what it means for the absolute value of f of x minus L to be less than epsilon. Remember, I spent a good amount of time on absolute values. This is equivalent to saying minus epsilon is less than f of x minus L is less than epsilon, which means capital L minus epsilon is less than f of x is less than capital L plus epsilon. Does that make sense? And so in absolute value notation, I have this. In graphical notation, I'm basically looking at this particular bandwidth. Okay? So I pick some random epsilon, what is this saying? What is this definition saying? How can I say that the limit as x goes to a is in fact L? Well, bless you. I have to figure out what value of delta I can find for which this would actually hold. So, what should I find for delta? Well, the idea is, whatever values I pick for x, f of x has to be contained within this bandwidth. That's basically the idea. Does that make sense? Well, think about this point where my, whatever this is, orange, crosses the axis, crosses the graph, and similarly when that crosses the graph. So, if I pick a delta, let's see, I'll use teal. Teal might not be the best color since you can't actually see it. Green. Still no? Blue. Okay? So, now what is this particular point right here? A plus delta. What is this point over here? A minus delta, right? What have I accomplished? Well, if you look at my graph, for any value in between my two blue lines here, my two blue dotted lines, if I go up, this is basically the graph that they're going to span. Well, notice this yellow is actually contained in this strip. Is that making sense? This is actually what the definition of a limit actually says. It says it in words, now it says it in a formula. Questions about this? Yes?
Okay, is the yellow area important to the problem?
The yellow is, the whole point of this particular problem is, as I said, given an epsilon, you have to find some sort of a delta for which all the values of your function are contained within this bandwidth. This is basically what it says. So what I'm showing is the fact that if I choose this delta, these are the values of my function, and they're well contained within my strip.
So that's the answer, pretty much, that yellow area?
Yes.
That's the end of the...
Well, no, the end is the fact that the limit is L.
Okay.
Yes?
This might be a really annoying question, but why are we finding a limit?
Of finding a limit?
Yes.
Well, there's 1,001 things of what of applications. I mean, one very simple application of limits is just there's a lot of real life things that you don't necessarily know what happens in the long future. For instance, one relatively simple example, and it has nothing to do with calculus, but I guess it's a simple thing of thinking about things. What are the odds of, if you flip a coin, you get a head? 0.5, right? You have half a chance of getting a head, half a chance of getting a tail, right? Which basically says there's something called the law of averages, the large law of averages actually, but nonetheless, flip a coin, take a coin and flip it 10 times. What are the chances of you actually getting 5 heads and 5 tails? As it turns out, not that much. Flip a coin 200,000 times. What are the chances of 100,000 of those are heads, 100,000 of them are tails? Chances are pretty good. And so the point is, you're interested in what happens in the long run. The idea is what happens further down the line, not necessarily in this particular instance. And this is just one simple example. You can think about like stock markets, for instance. You can think about a wide variety of things. Limits are actually quite important and interesting because the idea is what happens in the future is actually what you're interested in. For our personal purposes, one really big part of limits is derivatives. And the idea is what we're actually going to be after is what is the instantaneous rate of change. Like for instance the instantaneous velocity we looked at last time. and the instantaneous velocity, we basically defined it to be the limiting value of the average velocities. Right? We never actually got into that, when I looked at the problem, we never actually got into that 49 meters per second. We got close enough to it, and so we just assumed that the limiting value of that is going to be 49 meters per second, but we never actually proved it. We just said, well, the values kind of seem like they're actually getting to that, towards that value, so it's got to be that value. And we'll notice that the instantaneous rate of change of location is velocity. The instantaneous rate of change of velocity is acceleration, which are really real life, like physical concepts that you basically need limiting values for, which the name suggests you need limits. Is this making sense? And you can say no, because I know from personal experience that this is probably one of the hardest topics you've seen so far. Yes?
Okay, so how much of this actually involves math? Does it just involve...
No, this is just graphical. This is not a proof. This is just a graphical representation of what exactly does that actually mean. So my question is, do you understand what all of that means, basically looking at the graphical representation? We haven't actually used the definition to come up with the limit. I'm going to do that basically right now. I just wanted to make sure that you understand what is involved. Yes?
How can delta be the same if it's the distance from A? Like, I don't feel like epsilon would align the same parts away from A that delta is referring to there. Is that...
But see, that's the thing. My graph probably doesn't represent it well, but if you look close enough, notice that on the blue line, it actually crosses the line right there.
Right.
Yet the epsilon will cross the line there, like the horizontal line.
Oh, that's good.
And yes, I did it on purpose. The whole point is, you don't have to... Here, for all intensive purposes, I could find another interval that actually is half of that. It'll still work. As it turns out, delta is actually dependent on epsilon. For a given epsilon, this is exactly why the there is comes into play. For a given epsilon, you come up with a different given delta.
So what about L minus E? L minus epsilon right there, because there's nothing that has to do with that rolling down like this.
That's fine.
Okay.
It's a strict inequality, which means anything, as long as you're inside the interval, that's all you care. Here, before I go into real depth problems, so before I go into actually problems involving just letters, let's actually look at a real life problem, which is an actual problem, a simpler problem, which I believe 24. I assigned 24 for homework. I don't remember. I'm pretty sure I did, right? Okay, so let's do 23. So I have f of x equals 1 over x. So I need to find delta so that if the absolute value of x minus 2 is less than delta, then the absolute value of 1 over x minus 0.5 is less than 0.2. I guess I'm writing with blue. Don't know why. I guess to match my shirt. Is this making sense? I mean, do you understand what we're actually looking for? No? That's good. Okay. Well, I'm actually going through an actual example. Think about what this last line actually says. 1 over x is f of x. Right? A is 2. Right? Basically, what we're basically trying to claim is the fact that the limit as x goes to 2 of 1 over x is in fact 1/2. Everybody sees all the pieces where they're showing up? X minus 2, so the 2 shows up in the bottom of the limit. 1 over x, that's my function. 0.5, I just wrote it as 1/2 because it's a lot easier to see. Is that making sense? Now, we're not actually showing that this in fact is the limit. We're only saying, pick an epsilon. Can you find the delta corresponding to that? Which is exactly what I was just having on the picture for some, general epsilon. So picture-wise, because we also have a picture in the book, so we should use it. They used all that ink and all those graphing qualities over there, so. I guess I don't actually need this particular point over here. So let's see. If this is 1, this is 2. This would be 1/2. Actually, let me write it as 0.5. Okay. So now, what is actually my stuff in blue saying? It says that epsilon is 0.2. Do you remember how 0.2 actually shows up? Or do you remember how epsilon shows up in here? The idea is I'm looking for a width. So this would be 0.3 and that would be 0.7. Does that make sense? Everybody remembers this? Everybody understands this?
You can just pick random points?
In what sense? In what sense?
Like
Why 0.3?
7 and the 0.3, is that, oh, okay.
That's why I said if it makes sense. Remember, epsilon is 0.2, right? So the idea is the distance between these two has to be 0.2 in both directions. Okay, so now how do we find delta? Well, what are these values here? So if I bring them down, what is, I'll call this A, and what is B? A is 10 over 7, and B is 10 over 3. Is everybody understanding why?
No.
No? Well, think about this particular point. This point has coordinates x and 0.3. Right? But 0.3 is just 1 over x. This graph is the graph of f of x equals 1 over x. Right?
Just plug in.
Yeah, it's, I guess, the reverse of plugging in, but yes. Right, because I'm given y, I have to come up with x.
Plug in.
Right? Is everybody understanding this? Yes or no?
Okay. If you look at number 24, which intends that we have to plug in the x value into the equation to find the y value first.
No.
The A and B.
What did I just say? What is this actually saying here? I have x, I need y, I have y, I need x. Where are the question marks on 24? On the x-axis?
Yeah.
So which values of the x or the y you don't have?
You don't have the x values.
Okay? So how could you be plugging in x to come up with y? We have y, we need x.
You set y equal to.
So in our case here, y is equal to 1 over x. Right? Okay, well that means that 0.3 is equal to 1 over x, which means x is 1 over 0.3, which is 10 over 3. Does that make sense? Why 10 over 3? Because 0.3 is just 3 over 10. And you're taking the reciprocal of that. Is this making sense? Yes.
So, the red lines blue plus the blue lines at
I drew the blue lines where the red lines crossed the graph, because I wanted to identify what these points are. Okay?
Points have a relationship to delta?
Yes.
Are they delta?
Well, delta, remember, delta is symmetric in both sides of your value, right? So the question is now, what would delta be? So what we're saying is that A is 10 over 7 and B is 10 over 3, right? So then what should delta be? Four sevens? If you take 2 minus 10 over 7, you end up with 4 sevens. And if you take 10 thirds minus 2, you end up with 4 thirds, right? And the point is, you have to choose the smaller one.
Less than 2, right?
Well, because you're talking about symmetric sides. So if you think about it, my hand doesn't reach that far. So if you think about it, this distance is 4 sevenths, right?
Yeah.
This distance is 4 thirds. 4 thirds is over 1, right? It's clearly bigger than 4 sevenths, right? So if I were to choose this to be delta, then my interval would actually be this big, right? For any value that I pick, like for instance, if I pick 1, that'll shoot up to 1, which would be outside of my red line, my red strip. Okay? This is what I've done in the previous picture. The whole point was, you have to choose, whatever delta you choose, your vertical strip has to be contained fully inside. You know, when it crosses your original function has to be fully contained inside your red horizontal strip. Is that making sense? Yeah?
How do you write the answer?
Well, for this particular thing, you just have to find a delta for which that actually holds. So we can just say, after all of this, this means that delta equals 4 sevenths. And that's it. Or you can choose any other number less than 4 sevenths, and it'll work. So since 4 sevenths is a little bigger than half, you can choose half if you want to make your numbers look nicer. Is this making sense? In any shape or form? Yes.
Is that because 4 sevenths is within the red lines? Is that what you just said?
Because if you think about 4 sevenths, what you're going to have, and I'm going to use, I don't know what color to use. How about black, since I didn't use black for that. If you think about 4 sevenths, what is 2 plus 4 sevenths? 18 sevenths? 18 sevenths is going to be somewhere here. So what you're looking at is you're looking at this strip. Right?
Plus 4 sevenths and minus 4 sevenths?
Yes, that's what I was saying before. Remember it was A minus delta, A plus delta? And if you look at the strip going up, look at where it crosses the function. The entire function is contained within your red strip. Does that make sense? Yes?
So we always choose a smaller one?
Well, if by always you mean problem 24, then yes. Because, as I said, I started off slowly in the sense that we have some fixed epsilon. What we're going to do from this point on, starting with the next problem on, is say we're actually going to look at some random epsilon, which means we're never actually going to have numbers. And that's the joy of calculus, by the way. You know, there's a good amount of theory behind everything we're doing. I said joy, not bad. Okay, is this making sense?
Do a practice problem.
Okay, so let's see. What do you have for homework? Because I don't remember.
We have 24.
And then from 28 on, right? Something like that? No, from 30 on. I can take it out, I guess.
30, 32, 34, 42.
Okay. So let's look at. I don't know, 29? We have the limit as x goes to 1 of 2x plus 3 is equal to 5. In all of these problems, what you're supposed to do is prove that this limit is in fact equal to 5. Okay? And the only way to, the way to do that is using the epsilon delta definition. So this is basically the standard procedure. So let epsilon be bigger than 0. What do we need to find? So we need to find delta bigger than 0 so that if 0 strictly less than x minus 1 is less than delta, then the absolute value of 2x plus 3 minus 5 is less than epsilon. So far so good? Bless you.
Where does the expression
This is just the definition of the limit. Remember, it was 0 less than x minus a less than delta. Well, a you find right here. And then you have the absolute value of f of x, so I put f of x, minus L, less than epsilon. So all I did is basically just write out what we have in terms of the definition. Okay? Alright, so now, let's see. What else do we need to do? Well, here's the thing. We are given epsilon. We're saying let epsilon be bigger than 0. I don't know what it is, okay? But I have it. So the point is I need to find some sort of a delta that's going to be in relation to the epsilon for which this to hold. And so because epsilon is given to me, technically I have this relation, okay? So if I start working on the second relation that I have there, so if I look at the absolute value of 2x plus 3 minus 5 is less than epsilon, this is equivalent to saying the absolute value of 2x minus 2 is less than epsilon. Right? And it's equivalent to saying the absolute value of 2 times parenthesis x minus 1 is less than epsilon, which is equivalent to saying that the absolute value of x minus 1, or 2 times the absolute value of x minus 1 is less than epsilon, which is equivalent to saying that x minus 1 in absolute values is less than epsilon over 2. Too fast?
You can take the 2 out of the absolute, right?
Uh-huh.
Now, why is that?
Because of properties of absolute values?
I guess it is what it is.
Properties of absolute values say if I have the absolute value of a times x is equal to the absolute value of a times the absolute value of x. Whatever expression is x. It can be, in our case x minus 1 or whatever the case is. So if I take out the a, as long as I take it out as being positive, it's all good.
But it is a negative 2.
Yeah, it just comes out as 2. It comes out as the absolute value of a, which is 2.
Oh, okay.
So far so good? Yes?
How did the x minus 1 get into
I factor out a 2, so I'm left with x minus 1. Right? I'll tell you a secret, and we can do a couple more of these so you can see that the secret is in fact true. Whenever you deal with this part, your final answer will always involve the quantity you're looking after. Or I shouldn't say always, but it will always, as far as it's linear, it will always show up like that. Which means for problems 30, 32, 34, you should have that for every single one of them as far as the relationship.
Wait, we gotta graph this, right?
Yeah, I wouldn't worry about the graphing.
Wait, you don't want us to do it?
No, it's fine.
Alright.
Okay, is this making sense? So now what have we actually done? Look what we're actually looking for. We're saying, give me an epsilon. I need to find some delta for which if this relationship holds, then this relationship holds, right? If you look at this and stare at it for a couple of seconds, can you tell me what delta is? Epsilon over 2. Why? Well, notice that I put equivalents around every single one of them, right? So, if I choose delta to be epsilon over 2, what I'm saying is that x minus 1 in absolute values is less than epsilon over 2, right? But that's equivalent to 2x plus 3 minus 5 is less than epsilon. Which means picking delta as being epsilon over 2 gives me, in fact, this quantity. Which means I'm done. Which means let epsilon be bigger than 2. There exists delta equals to epsilon over 2, so that if 0 is less than the absolute value of x minus 1 is less than delta, which is equal to epsilon over 2, then the absolute value of 2x plus 3 minus 5 is less than epsilon. Is this making any sense?
So you're saying 0 is less than absolute value of x minus 1, that's all exponents, right? That kind of rule.
What do you mean?
Like, you said that all the answers for this problem is going to have an x minus 1 absolute value.
Not x minus 1. It'll have this quantity. That's that quantity. X minus 1 is just the fact that the limit was as x goes to 1.
Oh, okay.
If x was going to minus 15, then this would be x plus 15. Does that make sense? Your ultimate goal, and this is basically the key idea behind this, and this is exactly what we did in problem 23. The ultimate goal was we had this epsilon, right? Which in turns out actually was an actual number, and we found the corresponding number of delta that actually ended up being depending on epsilon. Right? Is everybody realizing that or no? Because remember what we did for 23. For 23, we said delta is going to be 4 sevenths. But how did I come up with 4 sevenths? Well, I looked at 2 minus that, and I looked at the distance between 2 and these 2 points. Well, how did these 2 points actually come about? I put an epsilon in for my function, right? That's basically the idea. That's where the connection comes into play. And so your ultimate goal for every single one of these problems is to find some sort of relationship, to find the absolute value of whatever you started with to be less than some quantity in terms of epsilon. That's basically the ultimate goal. As far as the functions being linear, which means like 30, 32, 34, that'll come out to be a situation of this nature. It'll be some sort of a, just going through the operations, it'll come up to something like this. If it's not linear, there's probably a little more work to be done. Yes?
So you're finding the interval of the bounds for a piece of the graph. What is that piece of the graph 24. Is that a tangent line? Is that what you're trying to find with that section of that graph?
No.
What's the relevance of that?
It comes into here. The whole point is you need to find a delta for which all your function, the distance from your function to your limit is within that epsilon. Which means all of the values of your function are going to be within those two bounds. So that's basically the idea.
Part of it as your limit goes to 1. Or whatever your limit is.
Well, yeah, if you get it in general terms, the whole point is that all the values that your x is allowed, and x is allowed these values, right? Because that's your restriction. For all those values of x that you're allowed, f of x minus your limit is within that bound. So the graph of f actually shows up in between those two bounds. Which is exactly what we said Wednesday in words, as far as I can make f of x as close as I want to L by making x as close as I need to A. That was basically what the definition in words said, which is exactly what we're saying here. Okay? Okay. Having fun so far? Now do you understand why I decided to spend more than one day on section 1.3?
So is our final answer the worded answer?
This is your final answer.
So how he wants to write it out?
Yes. Well, it's exactly how the definition is written. The only difference is we're actually saying what delta is in fact equal to. Right? The definition just says there exists a delta. And our goal is to find which one that is. Okay, more? More. Okay, let me give you a hint. 30, 32, 34. They all are basically done pretty much in the same situation as I just pointed out. Right? They're all linear functions. They all basically, the only thing you have to be careful with is the following. And I'm saying this because I've seen it on so many exams. If I look at, for instance, actually 35. Better yet, let me actually show it to you. 35 and 35. The limit, as x goes to minus 5, of the quantity 4 minus 3x over 5 is equal to 7. So again, the goal is to try and show this. Which, by the way, up to this point, we have no idea that this is in fact the case, right? I mean, if I would actually ask you to do this with the techniques that we've learned on Wednesday, you would basically have to start picking points around minus 5 and see what the values of your functions are, right? Which, remember, personally, that I found it to be extremely a lot of fun, right? Coming up with 15 different values of a table and then trying to come up with the numbers. I'm being sarcastic about that. So, as later on, as soon as we get to section 1.4, you'll find out that there's actually a much better way of doing things. But we need to actually develop the tools to get there. So what do we do here? So again, the same word comes to mind. Let epsilon be bigger than 0. We need to find delta, so that if 0 is strictly less than the absolute value of x plus 5 being less than delta, then what has to happen? 4 minus 3x divided by 5 minus 7 has to be less than epsilon. Right? Everybody understands where I got all these from? Yes.
So we know that the limit is 7, and we're just finding...
We're guessing that the limit is 7. We're actually proving that it is. That's basically the idea. And how do we guess that the limit is 7? As I said, big values close to -5, you kind of get the feel that the values are going towards 7. But as I said in the past, and as we looked at that particular example, right, when it looked like it's going to 1/6, but as we started getting smaller and smaller, it just exploded on us and went to 0, right? You might guess that it's true, but it might not necessarily be true. And so this is basically the only way to actually really prove that it is true. Yes?
So when a question is set in the form as the limit goes to -5 and the function equals number, that's really just a guess and finding bound to.
We're basically showing that it is, yes. The whole point is we're thinking that's the case, but we're trying to prove that it is the case. Okay, so what have we done in the past? What's the point? The idea is epsilon, even though it doesn't look like it is, we actually supposedly have it. We know what it is. So the point is we need to work with the right part to come up with the left one, right? That's basically what I've been saying, right? So let's work it out. I have the absolute value of 4 minus 3x divided by 5 minus 7 is less than epsilon. Well, this is going to be equivalent to -3 minus 3x over 5 less than epsilon. What do I do next?
Add the 3.
I can't add a 3 because I'm inside the absolute values. And I want to keep everything inside absolute values. So observe that I can take out a -3, so I can say this is equivalent to -3 times the parentheses 1 plus x over 5 is less than epsilon, right? So far so good? Okay. Now, how do I take the -3 out of the absolute value? It's just 3 times the absolute value of 1 plus x over 5, less than epsilon. And this is the part that I want you to be very careful with. In general, the tendency is to take out a -3. Okay? Sorry? It's absolute value, so you cannot have a negative, right? I mean, first of all, besides the actual theory that I told you that when you take it out, it has to be in absolute values, just think about what would it mean for a minus to be here. Well, that's obvious, right? I'm basically saying that -3 times the absolute value is less than epsilon. Well, clearly, because the left-hand side is negative. Why am I saying? I'm not saying anything. Is that making sense? Okay, so now what's the next step? Keep in mind our ultimate goal. Our ultimate goal is to come up with the absolute value of x plus 5 being less than some quantity. How can I do that? I can notice that this is equivalent to 3 times the absolute value of 1 over 5 times 5 plus x less than epsilon. Bless you. Which is equivalent to 3/5 times the absolute value of 5 plus x being less than epsilon, which is equivalent to saying that the absolute value of x plus 5 is less than 5 epsilons over 3. Is it okay? Yes.
How'd you get there?
X plus from where? From here to here? Again, the key idea is x plus 5. That's my ultimate goal. I have 1 plus x over 5. I don't have x plus 5. But I can notice that if I take out a 1/5, I'll end up with x plus 5. You know, basically just think about the fact that if I'm multiplying the inside quantity by 5, I end up with 5 plus x, which is x plus 5, right? So if that's the case, then a 1/5 taking it out is going to accomplish the same goal. So far so good? So what is delta? 5 epsilon over 3. Does that make sense? So the idea is we set this to be delta. So now let epsilon be bigger than 0. there is delta equal to 5 epsilon over 3, so that if 0 is strictly less than x plus 5 is less than delta, then, which equals 5 epsilon over 3, then the absolute value of whatever it was, let's see if I can pick it up without 4 minus 3x over 5 minus 7 is less than epsilon.
Is this it for 1.3, this concept?
Yes. Is this making sense? Okay. 40 and 42 are going to be a little tricky. 38 is going to be very easy and obvious. But I'll let you actually discover that. It is literally very simple. You just basically have to write out exactly what the definition is. Remember how I start off. Remember what's the first thing that we start off with. Right? This is the part that I started off with. So for all of these problems, that's the first thing that you want to do. Just write that out. Okay? I'm going to do 37. So 38 says that the limit as x goes to a of a constant is in fact equal to the constant. So this is basically what you're going to have to show. And as I said, it's actually very straightforward. All you have to do, and I'm not saying it's really easy just because, you know, I know this stuff. Literally, if you write out your definition, it'll just literally come out. Okay? What I'm going to look at right now is 37. What is the limit as x goes to a of x? Well, what we're going to try and show is the fact that it's equal to a. And as it turns out, this is also incredibly easy. Why is it easy? Well, what's the definition? Let epsilon be bigger than 0. We need to find delta bigger than 0, so that if 0 is strictly less than the absolute value of x minus a is less than delta, then x minus a is less than epsilon. What is delta? Epsilon. Is everybody seeing that?
Yeah.
So just think about the fact that if this was easy, the other one should be even easier. Yes?
In the definitions, are epsilon and delta always bigger than 0?
Yes. Well, just think about what it means. You're trying to set both of them being bigger than an absolute value. Absolute values are always positive, so it wouldn't make any sense to have a negative. So, epsilon is equal to delta, or delta is equal to epsilon, however you want to look at it, right? Because we have the same quantity. We achieve the goal without actually doing any work. Does that make sense?
Yeah.
Okay.
Boy, do you want us to write out the end part? Like that's like the beginning and the end.
For this particular problem, it doesn't matter because there's really nothing we've done. We're just basically saying the same thing. So I wouldn't necessarily worry for this one, but in general, yes, you have basically say the whole statement because that's what you're really trying to show. Just by saying epsilon is equal to something or delta is equal to something doesn't really mean much. Kind of like on the same token as, you know, I ask you what the domain is and you tell me x cannot equal 1. Okay, I understand that, but what else am I actually meaning? Okay? Alright, let's see. 41. We have the limit as x goes to 0 of the absolute value of x equals to 0. So our goal is to show that the absolute value of x goes to 0 as x goes to 0. So how do we show that? Well, as it turns out, we can technically use the definition. Right? I basically can say, let epsilon be bigger than 0. We need delta bigger than 0, so that if the absolute value of x is bigger than delta, I guess 0, then the absolute value of the absolute value of x minus 0 is less than epsilon. Right? This is exactly the definition. Does that make sense?
No,
Why not?
I don't understand the absolute value of an absolute value.
All I'm doing is writing the definition. I'm saying the absolute value of f of x minus L.
Okay,
That's f of x minus L.
that's just it.
But now the question is, what's the absolute value of an absolute value?
That's just the same thing.
So first of all, subtracting 0 doesn't actually change anything. So I have the absolute value of x being less than epsilon. But taking the second absolute value of a first absolute value doesn't change absolutely anything, because the first absolute value just gives you the positive of that, right? Which means this is equivalent to the absolute value of x being less than epsilon. So what is delta? Epsilon, right? Does that make sense? So for every epsilon bigger than 0, there is delta, which equals epsilon, so that if 0 is less than the absolute value of x is less than delta, then the absolute value of x minus 0 is less than epsilon. Maybe I should spare you.
Yeah, please.
How about you don't have to do 42? Because personal past experiences showed me that I'll end up doing 42 on Wednesday anyway. So I might as well save myself
Yeah, why don't we do it now?
we can do it now if you want. Okay. Notice one thing about 42. Look at what the limit is actually asking you to do. It says the limit as x goes to 9 minus, which means we're actually looking at a side limit, not an actual limit. Right? A side limit? Yeah, remember the minus and the plus? We talked about it on Wednesday. So 42 and 35. Notice we managed to pass the number of problem versus the number of page. Later on, that's not going to happen anymore. Limit as x goes to 9 minus of the fourth root of 9 minus x is equal to 0. So first of all, we never actually defined side limits. Right? So, what is the actual definition? Well, it says the following. For epsilon bigger than 0, there is delta bigger than 0, so that, remember originally, and I'll put it in a parenthesis just so we have it, this is the original definition, right? It said if 0 strictly less than the absolute value of x minus a is less than delta, then the absolute value of f of x minus L is less than epsilon. Right? How would be the left side limit would work? Bless you. For a second, I'm going to roll all the way up. Remember what left and right limits are. The idea is you can get to the point from both directions, right? If I'm looking at a left limit, it means I'm only coming from the left direction, right? Which means instead of having both of these satisfied, I'm only looking at this strip. Only left side of A. Which means, coming down here, what do I have? Well, I will have that A minus delta is less than x is less than A. Right? So if that happens, then the absolute value of f of x minus L is less than epsilon. Right? Is this making sense? Yes.
All right. I understand the left part, right? 0 less than f value of x minus a. Because that's how we do the problem. Switch everything. I don't understand the f of x minus L.
Why not? I mean, why are you understanding the first part and not the second? What do you understand about the first part?
Because the first part is what we do to solve the problem. It's almost like just plugging stuff in and then using the equation to find epsilon. But the second part of the equation, or the second thing right there, just kind of sits there. I don't know what it means.
Well, we're actually using the second part to come up with the first part. Are we not? That's how we always start. We always start with this, and you work our way to that. Right? Let me pull it up. What do we start off with?
4 minus 3.
What is the first thing that I do? I take the right hand side and I keep working it until I'm trying to get to the left hand part. So it stays there in the sense that we don't change it at the end, but we're using it to come up with delta.
Okay, so L is negative, it was 7, right?
Yes.
Okay, okay.
Alright, so now coming back to 42, notice that I actually was able to eliminate absolute values as far as the left hand side is concerned, but I can't really do anything about the right hand side. Do you know why? Yes?
Because epsilon has to be positive.
Well, epsilon has to be positive, but the reason why I have to keep the absolute values is the fact that I have no guarantees that if I take out the absolute values, that's what would automatically imply that f is increasing, which is something that I don't know. I don't know how my function is going to behave getting into L. Okay? So it could be higher or it could be lower than L. And so I have to still keep it in terms of absolute values. Do you understand what I'm saying? Okay, so what is our next move? Plug in what we know?
Yeah.
Right? So if, let's see, 9 minus delta is less than x is less than 9, then the absolute value of the fourth root of 9 minus x is less than epsilon. I skipped the 0 part. Should I write minus 0? Minus 0. Minus 0 in absolute values is less than epsilon, right? Again, all I'm doing is just writing up what I know. So now let's take the fourth root of 9 minus x to be less than, in absolute values, less than epsilon. Well, fourth roots by definition are positive, or non-negative I should say, right? Which means this is just the fourth root of 9 minus x being less than epsilon. Okay? So now what next?
Oh, wait. The absolute value of the square root is, you can just remove the absolute value.
But by definition, square roots are positive. Absolute values make things positive.
Okay.
So if I have something positive, then double positive is still positive. Yes.
Are we trying to find
Yeah, no, for the
Delta.
plus 9 equals epsilon? Or is
We're trying to find delta.
that what the range is for that? Plus 9?
Sorry, say that again?
What are we trying to factor this out into? We're not factoring
This one?
simplify it into, yeah.
Well, we're trying to get to something like this, of this nature, something that kind of, helps us out in figuring out what, delta might be. And so, the one thing to identify here is the following. What happens if I take, so first of all, notice one thing. Fourth root of 9 minus x, when would that make sense? When x is bigger than 9? Sorry, less than 9? X is less than 9. Means that's actually satisfied, right? So the quantity underneath the fourth root is always positive. Epsilon is always positive. What happens if I raise to the fourth power? I end up with 9 minus x being less than epsilon to the fourth power. Right? Now keep in mind, x is bigger than, is less than 9. And this is actually important because if it's not less than 9, then this makes no sense. Right? Epsilon is a positive quantity. I can't have a negative number. I guess I can, but it's pointless. So now from here, what I need to get to is this part. And so, what do? Well, from here I notice that x is bigger than 9 minus epsilon to the fourth. Right?
Yeah.
Is that making sense? X moved to the right, epsilon to the fourth, moved to the left, and I guess I wrote it the other way, the inequality. Too fast?
Where did we just go?
From here to here.
Okay. We just kind of switched stuff. Okay.
Take an extra step.
Yeah, I got it.
Is everybody understanding this?
Yes.
Okay, so what is epsilon? What is delta? What is delta? A minus delta has to be less than x. So what is delta? Epsilon to the fourth. A is 9.
Just do it too.
So, for every epsilon bigger than 0, there is delta equal to epsilon to the fourth, so that if 0 well, I guess we're looking at a side limit. If 9 minus delta is less than x is less than 9, then the absolute value of the fourth root of 9 minus x minus 0 is less than epsilon. Now, the only thing I should probably point out is why in the world are we actually looking at a side limit? And the answer is, if this is minus, wrong thing. If this is 9, this is my graph of the fourth root of 9 minus x. Which means I can't talk about a right-hand limit because my function is not defined there. Yes?
Okay, so since we have 9 minus delta, and then our end answer is 9 minus
epsilon to the fourth.
we just epsilon to the fourth, we just take out the 9 minus because that's already...
Well, you match them. 9 minus epsilon to the fourth has to be the same as 9 minus delta.
Yeah.
So...
Okay, so then delta is... Okay.
And again, the whole point is this was an equivalence, so you just come, kind of go back up and, pick it up. I'm glad I got a chance to talk about section 4. Okay, we have 5 more minutes, and I should probably do that. Just so you feel like, you should go into the break thinking a little better about yourself, since I'm sure you really love this stuff. I'm being sarcastic, or I'm being ironic, because I know again from personal experience that this is actually, and this is probably one of the hardest concepts that we're going to learn this semester. Okay, so I'm not saying things are going to get a lot easier, but I'm not saying that, don't go home and think, if section 3 is like this, what in the world is chapter 4 going to be, or whatever, the situation may be. Things are going to get a lot easier, actually. It's at some parts, and then more complicated and so forth. Yes?
So what is this matchup again?
First line says what we're actually looking at, right? We're looking at if that holds, then that holds, right? So again, what we're doing is we're starting with the right side, and we're trying to come up with a delta. So we're trying to come up with the left side, basically, right? So in the process, we figured out that x can't be bigger than 9. So that satisfies half of it, right? And then again, in the process, we came up with this identity. And I probably should have wrote it the other way around, but the idea is 9 minus epsilon to the fourth is less than x. So if you come back up, then epsilon to the fourth is in fact delta. Because you have 9 minus epsilon, 9 minus 9 minus delta and 9 minus epsilon to the fourth are basically the same kind of idea. Okay? Alright, so now, yes?
So, starting from the beginning of that, we only have like one epsilon line and one delta line since the side limit.
No, see, that's the thing. This is why I said we have to maintain the absolute values. You only have one side for the delta, but you'll have two sides for the epsilon, because your function can be either increasing or decreasing. So the idea is, if you think about your bandwidth, right? If you think about the bandwidth that you had, let's say this is A, and then this is L. Your function could be behaving like something like that. Which means you have to talk about absolute values, you have to talk about distances. You can't just say, f of x minus L, because then that'll only give you the bottom part.
So we know the domain, but we don't know where the range is.
Yes. Okay, limit laws. As I said, I would like to finish this off with a different perspective on things, just so you kind of see how things work. So, assume the limit as x goes to a of f of x, and the limit as x goes to a of g of x exist, and c is a constant. Part 1 says the limit as x goes to a of the function f of x plus or minus the function g of x is equal to the limit as x goes to a of f of x plus or minus the limit as x goes to a of g of x. Part 2, the limit as x goes to a of a constant times f of x is equal to the constant times the limit as x goes to a of f of x. Three, the limit as x goes to a of f of x times g of x is equal to the limit as x goes to a of f of x times the limit as x goes to a of g of x. And the last one says that the limit as x goes to a of f of x divided by g of x is the limit x goes to a of f of x divided by the limit as x goes to a of g of x, as long as the denominator is not 0. So, as long as the limit is not 0. There's a lot more properties, and we're going to go through a lot more of them next time. But the reason why I'm pointing these out is, as I said, to give you a kind of a nice feel at the end. Do you remember what the limit as x goes to a of c is? This is what you have to show, that it's c. And we also said that the limit as x goes to a of x is equal to a, right? I showed you the second one. So then, with these in mind, and with the properties above, can you tell me what the limit as x goes to 2 of 4x minus 3 is? Eight minus 3, which equals 5. Why? Well, because the first property we have is it says that the limit of a sum is just the sum of the limits, right? Or a difference. So as a first thought, you can separate 4x minus 3 in the limit of 4x minus the limit of 3. The limit of 3 is just 3 based on this. The limit of 4x based on property number 2 is 4 times the limit of x, which is just the limit of x is just 4. Sorry, it's just 2. So you end up with 4 times 2 minus 3, so you end up with 5. And because we use the definition of a limit to show these, and we know they're true, and with all of these, that means that we can actually solve these in a much easier way, and we don't have to involve the epsilon deltas. For some of them anyway. So I just figured I should, as I said, give you something to have that looks a lot easier than just the epsilon delta definition.